Welcome to Calm and Clever. It's lovely to have you here tonight. So before we begin, let me ask you the question I always like to ask. Where in the world are you listening from? Maybe it's late where you are, the kind of late where the house has gone quiet and the only light left is the one beside you. Maybe it's a city with the soft hum of traffic far below. Maybe it's somewhere out in the country where the dark is real dark, the kind you can feel. Wherever you are, whatever the hour, settle in, get comfortable, pull the blanket up if you have one. There's nowhere you need to be and nothing you need to do for the next little while except let your mind drift wherever it likes. And if you enjoy these slow journeys and you'd like more nights like this one, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me rely on that more than you'd think. And to those of you already subscribed who come back night after night, thank you. Truly, means a great deal. Now here's my usual little warning. I'm going to try very hard not to make tonight so interesting that it keeps you awake. But I can't make any promises because the thing we're going to talk about is genuinely strange and a little bit haunting, and very beautiful in the way that only the universe seems able to manage. So if it does keep you up, well, at least you'll have learned something. A fair trade, I think. And if you drift off before we reach the end, that's perfectly fine. That's actually the whole idea. The ideas will still be here in the morning. The star we're talking about will still be there tomorrow night, and the night after that. Exactly as it's been for every human being who has ever looked up. You don't need to hold on to anything. You don't need to understand every piece. Just let it wash over you, slowly, the way the tide comes in. So, let me tell you something, and I'd like you to picture it as I do. Imagine a single spoonful, an ordinary teaspoon, the kind you'd stir into a cup of tea before bed. Picture it sitting in the palm of your hand. Now imagine that on that little spoon, taking up no more room than a thimble of sugar, there sat a piece of a certain kind of star. Not the whole star, just a spoonful of it. A taste, that spoonful would weigh several tons. Sit with that for a moment because it doesn't make sense, and it isn't supposed to make sense, not yet. Tons. The weight of a car, the weight of an elephant, maybe more. Resting on a single teaspoon, you could close your hand around. If you somehow had it here in the room with you, it wouldn't sit on the spoon at all. It would tear straight through the spoon and through the table and through the floor and keep going because there is nothing made of ordinary matter. Nothing in your house, nothing in your whole city strong enough to hold a spoonful of this stuff up. And here is the part that I find quietly astonishing. The star this spoonful comes from is not hidden away in some distant, invisible corner of the cosmos. It is not some obscure thing only astronomers have ever heard of. It is, in a sense, hiding inside the most familiar light in the entire night sky. It's tucked right up against the single brightest star you have ever seen with your own eyes. Because here's the secret we're going to unfold tonight, slowly, one gentle thread at a time. The brightest point of light in our entire night sky, the one our ancestors named and worshipped and built calendars around, the one you've almost certainly seen yourself on a clear winter evening without even knowing what you were looking at, that brilliant, dazzling point of white fire is not one star at all. It's two. And one of the two is dead. The brightest light in our sky is, in part, a corpse, a stellar corpse, the cooling, crushed remains of a star that died long before any of us were born, long before there were any of us at all. It is sitting right there beside its living companion, faint and small and almost impossible to see, and yet weighing as much as our own sun. And the most wonderful part of all, the part we'll spend our time together drifting through, is this. We knew that dead star was there before any human eye ever saw it. We found the body, you might say, before we ever found it in the sky. We read the death certificate first, and only later went looking for the grave. But I'm getting ahead of myself. We have all night. Let's slow right down and start where we should start, which is with the star you can actually see, the bright one, the living one. Let me introduce it to you properly. Its name is Sirius. You may have heard the name before. It has a lovely sound to it, doesn't it? Sirius. It comes down to us from the ancient Greek, and there are old hints that it once meant something like scorching or glowing or searing, which feels exactly right when you see it, because Sirius does not twinkle politely the way most stars do. Sirius blazes. On a cold, clear winter night, low in the sky, it can flash and flicker in violent colors, blue and white, and even flashes of red and green, like a tiny diamond someone is turning over and over in the dark. That flickering is just our own restless atmosphere bending its light, the warm and cool air shuffling about between you and the star. But it makes Sirius unmistakable. Once you've truly seen it, you never confuse it with anything else. Astronomers have a more formal name for it, a sort of full title, the way you might have a long official name on a document somewhere, even if everyone just calls you by a nickname. Sirius's official name is Alpha Canis Majoris. Now that sounds like a mouthful, but it's really just a tidy little address, and I want to unpack it for you gently because every piece of it tells you something. Canis Major, that's Latin, and it means the greater dog. Sirius lives in a constellation, a pattern of stars that the ancients pictured as a large dog, the greater dog following at the heel of the great hunter, Orion, across the winter sky. And Sirius, this brilliant blazing point, sits roughly where the dog's heart or chest would be, which is why for thousands of years, in language after language, Sirius has been known by a simpler, warmer name, the dog star. Hold on to that, the dog star, because it'll matter later, in a way I think you'll find rather sweet. And the first word, alpha. In astronomy, the brightest star in a constellation is very often given the label alpha, the first letter of the Greek alphabet. Indeed, the way you might number the most important thing first, Alpha Canis Majoris, the brightest star of the greater dog. And it earns that title many times over because Sirius isn't just the brightest star in its own little patch of sky. It's the brightest star in the whole sky, brighter than any other star you can see from anywhere on Earth on any night of the year. Now, astronomers like to measure brightness, and they have a slightly funny old system for it that goes all the way back to the ancient Greeks. They call it magnitude. And the strange thing about magnitude, the thing that trips everyone up at first, is that it runs backwards. The brighter a star is, the smaller its magnitude number. The faintest stars you can just barely see on a dark night sit up around magnitude 6. The brighter ones drop down toward 1 and 0. And the very brightest objects go into negative numbers. Sirius shines at a magnitude of about minus 1.46, minus 1.46. That deep into the negatives is rare and special. To give you something to compare it against, picture the second brightest star in the whole night sky, a star called Canopus, far down in the southern skies, a magnificent star in its own right. Sirius is brighter than even Canopus, roughly twice as bright in fact, twice as bright as the runner-up. Sirius doesn't just win the race for brightest star in our sky. It wins it comfortably by a wide and easy margin, the clear and undisputed champion. So you might be lying there now, and a perfectly reasonable thought might be drifting through your mind. You might be thinking, well, of course it's the brightest. It must be the most enormous, most powerful star out there, a colossal furnace dwarfing all the others. And that's a natural thing to assume. But it isn't quite the whole story, and the real reason is gentler and, I think, lovelier than that. Sirius is bright for two reasons working together like two voices in harmony. The first reason is that yes, it genuinely is a luminous star, a real and impressive thing, brighter than our own sun by a good margin, as we'll come to. But the second reason, and in many ways the more important one, is simply this: Sirius is close to us. Close in the way that the candle on your own bedside table looks brighter than a floodlight a mile away, not because the candle is more powerful, but because it's near. Sirius is one of our near neighbors in the vast dark. It sits about 8.6 light-years away from our sun. Now, a light-year is one of those phrases we hear so often that it can lose all its meaning. So let me slow down and give it back to you, gently. A light-year is not a measure of time, even though it sounds like one. It's a measure of distance. It's the distance that a beam of light travels in one whole year. And light is the fastest thing there is. It crosses the entire width of our Earth in the blink of an eye, less than the blink of an eye. It races from the sun to us across that whole enormous gulf in about 8 minutes. And yet to travel a single light-year, that same unimaginably fast beam of light has to keep going, without rest, without slowing, for an entire year. And Sirius is 8.6 of those away. The light that's reaching your eyes when you look at Sirius on a winter night left that star more than 80 years ago. It set out across the dark while you were a slightly younger version of yourself, traveling all that time just to arrive, finally, tonight, at the back of your eye. There's something tender in that, I always think. You're never quite seeing the star as it is. You're seeing a letter it sent years ago, only now arriving. But in the grand scheme of the galaxy, with its billions upon billions of stars scattered across distances so vast the numbers stop meaning anything, 8.6 light-years is practically next door. It makes Sirius part of a very exclusive little neighborhood. In fact, the Sirius system is the 7th nearest known stellar system to our own solar system, the 7th closest of all the countless stars in the sky. Out of all of them, only a small handful of stellar systems sit closer to us than Sirius does, and that closeness is a big part of why it blazes so. It's a genuinely fine star, yes, but it's also right here, nearly on our doorstep, cosmically speaking. A bright candle held close, that's our Sirius. So let me draw the picture as it stands so far. The tidy, settled, sensible picture. The one that any astronomer of a couple of centuries ago would have happily given you. There is, low in the winter sky, in the constellation of the Greater Dog, a single, brilliant star called Sirius. The brightest in all the heavens. Twice as bright as its nearest rival. A near neighbor, only 8.5 light-years off. A clean, simple, magnificent point of white-blue fire. One star. It's a lovely picture, it's neat. It's the picture humanity carried for thousands and thousands of years. And it is, as we're about to discover, quietly, profoundly incomplete, because that single point of light is not single at all. Let me linger here for a while, because this is the heart of the whole night, and I don't want to rush past it. When you look up and you find Sirius, when you pick out that one fierce, flashing star, your eye tells you a very confident thing. It tells you, here is a star. One star, a single source of light. And your eye is not lying to you exactly. It's just that your eye, marvelous as it is, simply isn't sharp enough to see the truth that's hidden in that brilliance. Because right there, impossibly close beside that blazing point, so close that the two of them merge into one in your vision, there is a second star, a companion, a partner. The two of them are bound together, locked in a slow and patient gravitational embrace, circling one another the way two dancers might turn slowly around a shared center, holding hands across the dark. They have been turning around each other for ages beyond counting, and they will go on turning long after we're gone, and the two partners could not be more different from one another. They are the strangest pair you could imagine. One of them is young and dazzling and very much alive. The other is something else entirely, something quiet, something dead, something that should not, by all the ordinary rules you know about the world, be able to exist at all. The bright one, the one you see, has a name now. We call it Sirius A, the big, luminous, living star, the one doing all the blazing. That's the one your eye finds. That's the dog star, you know. And then there is the other, the companion, the one your eye has never seen and never will, not without a serious telescope and a clear night and a great deal of luck. We call it Sirius B, and Sirius B is the dead one. Sirius B is our corpse. Sirius B is where that impossible teaspoon comes from, the one that weighs several tons. Sirius B is a kind of star called a white dwarf, and tonight, slowly, we are going to understand exactly what that means and why it's one of the most genuinely bizarre objects in all of nature, and how on earth we ever came to find it, sitting there, invisible beside the brightest light in our sky. But I'm running ahead again. I do that when something's exciting. Let me pull us back and let me just hold us here a moment in the simple wonder of it before we go any deeper, because I think it's worth feeling before we explain it. Think about it like this. Every civilization that has ever lived on this earth has looked up at Sirius. Every one. The ancient Egyptians watched it, and it mattered enormously to them, more than almost any other star. The Greeks named it. The Romans wrote about it. Sailors steered by it. Farmers timed their seasons by it. Children, for thousands of years, have pointed up at it on cold, clear nights. Billions and billions of human eyes across every age of our history have rested on that one brilliant point of light. And not a single one of them, not one, for the vast and overwhelming majority of human history, had any idea that they were looking at two stars. Not one of them knew that nestled right up against that brightness was a tiny, dense, dead companion, the crushed remains of a star, a thing as heavy as our sun, packed into a ball the size of our own Earth. It was there the whole time, hiding in plain sight, hiding inside the most famous light in the sky, right there in front of every pair of eyes that ever looked, and invisible to all of them. There's something almost dizzying in that, isn't there? That something so strange, so extreme, could be right there in the most obvious place imaginable, the brightest spot in the sky, and we never knew. It makes you wonder, gently, what else is hiding right in front of us? What else have we been looking straight at all this time without seeing? But let's not wander into worry. We're here for calm, and there's nothing here to fear, only to marvel at. So let me ask you to do something for me if your eyes are still open. Let me ask you to really picture Sirius up there in the dark. Hold that single bright point in your mind. And now, very gently, I want you to imagine that you could see closer. Imagine your eyes had the power of a great telescope, that you could lean in toward that blazing point as though leaning toward a candle flame to see it better. And imagine that as you drew nearer, the single point of light slowly, softly split, drifted apart into two. There it is. The big one, fierce and white and brilliant, Sirius A, the living star. And then, off to one side, painfully faint, almost lost in the glare of its dazzling partner, a tiny ember, a small, pale, lonely point. Sirius B, the pup, as it came to be called, though we'll come to that story, the dead one, the corpse, the teaspoon that weighs tons, holding its place beside the brightest light in our sky, the way it has for ages, patient and silent and unimaginably strange. That faint little ember is what we're going to spend tonight getting to know. And I want to be honest with you right from the start about why this is going to be such a satisfying thing to drift through, because there are really two great mysteries braided together here, two stories that will unwind side by side, and either one alone would be worth a whole night's wondering. The first mystery is the impossible nature of Sirius B itself, the physics of it, the sheer, almost absurd extremity of the thing. How can a star be as heavy as our entire sun and yet be squeezed down to the size of a small planet? What is it actually made of that a spoonful weighs tons? Why doesn't it simply crush itself out of existence under its own monstrous weight? It isn't on fire, you see. It isn't burning the way our sun burns, the way Sirius A burns. There's no furnace inside it holding it up against the crush of its own gravity. And yet it doesn't collapse. Something holds it, something stranger than fire. We'll come to what that something is, and it turns out to be one of the deepest and most surprising rules in all of nature, a rule about the very smallest building blocks of matter. That's the first mystery, the mystery of the corpse. And the second mystery, the one I find almost more wonderful, is the story of how we ever knew it was there at all. Because remember, you cannot see Sirius B with your naked eye. It's far too faint, and it's drowned out completely by the brilliance of its bright companion sitting right beside it. The glare of Sirius A simply swallows it whole. For all of human history, it was utterly invisible. So how, then, did anyone ever come to suspect that it existed? How do you find something you cannot see, a star hidden in the glare of a brighter star, a dead thing tucked invisibly behind a blaze of light? And the answer is a true detective story, a genuine piece of cosmic forensics, more than a century and a half old now, and I think it's one of the most beautiful examples there is of the human mind reaching out and grasping something that the human eye simply could not. Because a single, very clever astronomer, sitting at his desk with nothing but careful measurements and patient mathematics, looked at the way Sirius moved across the sky, and from that motion alone, from a tiny, subtle wobble in its path, he concluded with confidence that there must be something there. Something massive, something invisible. Something tugging at the bright star, pulling it gently off its course like an unseen hand. He never saw it. He never could. But he knew it was there. He worked out where it must be and how long it took to circle and roughly how heavy it had to be, all of it from a wobble. And then, years and years later, long after he had done his work, someone finally pointed a great new telescope at exactly the spot he had implied. And there it was, a faint little point of light, sitting right where the mathematics had quietly promised it would be all along. Imagine that for a moment as you lie there. Imagine being so sure of something you cannot see that you can tell the world exactly where to look, and how long it will take to go around, and have it turn out to be true, confirmed by a telescope years down the line. Imagine pointing at a patch of seemingly empty sky and saying calmly, there is a hidden, massive, invisible thing right there, and being right. We'll walk through every step of how that was done, gently, because it's a story worth telling slowly, and because the way it was done is in some ways even more remarkable than the thing it found. So those are our two threads for tonight. The impossible physics of the dead star and the detective story of how we found it without ever seeing it. And we'll braid them together slowly, the way you'd plait a rope, going back and forth between them, until by the end the whole picture sits clear and complete and, I hope, leaves you with that particular flavor of calm that comes from understanding something strange and beautiful about the universe you live in. But there's no rush, none at all. We have the whole night. So for now, let's just stay here, gently, with the simple shape of the secret. The brightest star in our sky is not one star, it is two. The dazzling Sirius A, alive and brilliant and near, and the faint, hidden, impossible Sirius B, a dead star crushed to the size of the Earth, as heavy as the sun, with a teaspoon that weighs tons, holding its quiet place in the glare for ages, unseen by every eye that ever looked up, until the day a careful mind reached out and found it in the dark. Let me say a little more about just how stark that difference is between the two of them, because I don't think I've quite given it to you yet, and it's the kind of contrast that's worth resting in. Sirius A, the bright one, is a young and vigorous star. It's what astronomers call a main sequence star, which is simply the long, stable, healthy middle of a star's life, the great calm stretch where a star sits comfortably and burns its fuel steadily. The way our own sun is doing right now, the way it will go on doing for billions of years. Sirius A is bigger than our sun, around twice as massive, and it shines a good deal more fiercely, something like 25 times more luminous than the sun. It's a hot, bluish-white star, brimming with energy, in the prime of its long life. If you could stand it next to our sun, it would look bigger, brighter, hotter, more dazzling in every way. A magnificent, living thing. And then there's its partner, right beside it. As heavy as our sun, more or less, every bit as much matter, the same vast quantity of stuff. But instead of being spread out across a great glowing sphere of a star, all of that mass, all of that sun's worth of material, has been squeezed and crushed down, down, down into a ball no bigger than the planet you're lying on right now, the Earth. Take the sun, crush it to the size of the Earth. That's Sirius B. That's the corpse. Sitting there, faint and small and almost unbelievably dense, beside its blazing living twin. A great hot living star and a tiny crushed dead one, bound together, turning slowly around each other in the dark, 8.5 light years away, for age after age after age. And to your eye from here, the two of them are nothing but a single point of fierce white light, the brightest one in the sky. I find I keep coming back to that word, hidden, because that's really what tonight is about, in the end. The hidden thing inside the obvious thing, the corpse inside the brilliance, the strangeness tucked away inside the most familiar light there is. So as we go on, and we will slowly, I'd like you to hold two feelings together, gently, the way the two stars hold their orbit. The first feeling is wonder at the thing itself in this impossible crushed dead star, heavier than you can imagine, denser than anything you've ever touched. And the second feeling is wonder at us, at the patient, clever, persistent human minds that manage to find it, to weigh it, to map its slow dance, all without ever being able to simply look at it. Both of those are worth a whole night's quiet marveling, and we have the whole night, so we'll give each of them their time. Let's begin to move toward the detective story now gently, because that's where the trail starts, with a single careful man and a star that wouldn't move in a straight line. But first, let me set the stage for him, because to understand what he noticed, you have to understand a small and lovely fact about the stars, one that's easy to miss. We tend to think of the stars as fixed, pinned in place. The very phrase, the fixed stars, comes down to us from the ancients, who pictured them as little lights set into a great unmoving dome, turning overhead each night but never shifting their patterns. The constellations look the same to you tonight as they look to the Egyptians and the Greeks and to everyone in between. The greater dog is still the greater dog. Sirius still sits in its heart. Nothing seems to move, but that fixedness is an illusion, a gentle trick of distance and time. The stars are not fixed at all, they are all in motion, every one of them drifting through the galaxy on their own long, slow paths, like a great scattered crowd, all walking in slightly different directions across an impossibly wide field. It's just that they are so unimaginably far away that their motion across a human lifetime, or even across many human lifetimes, is far too small for the naked eye to catch. A star might shift by the tiniest fraction of a degree over a whole century. So to us, Watching, they seem to stand perfectly still. But they don't. They drift. Slowly, ceaselessly, they drift. And Sirius drifts too, of course it does. And because Sirius is one of our nearest neighbors, so close, only 8.5 light years off, its drift across the sky is actually a little easier to notice than most. A nearby thing seems to move faster than a distant one, the way a bird flying past your window seems to streak across while a far-off plane seems to crawl, even though the plane is moving much faster. So Sirius, being near, has a relatively noticeable drift, what astronomers call its proper motion, its own true movement across the sky, slow but real, measurable if you watch it carefully and patiently over many years. And here is the small, strange thing that started everything. Here is the loose thread that, when pulled, unraveled the whole secret. When astronomers in the early 1800s began to track that drift, carefully, precisely, year after year, plotting exactly where Sirius sat against the more distant background stars, they found that its path was not quite right. Sirius was not drifting in a straight line. It should have been. A lone star drifting through space ought to trace a clean, straight path across the sky, steady and true, like a single marble rolling smoothly across a level floor. That's what you'd expect. That's what the simple, tidy picture demanded. One star drifting straight. But Sirius wasn't doing that. When they looked closely, when they measured carefully and plotted its position over the years, they found that its path wasn't a straight line at all. It was a wave, a gentle, subtle, side-to-side wobble. The star was weaving ever so slightly as it drifted, swaying a little to one side and then a little to the other, tracing out a faint, wavy ripple across the sky instead of a clean, straight road, as though something, somewhere, were gently tugging on it. First this way, then that way, over and over in a slow and regular rhythm. And that little wobble, that refusal of the brightest star in the sky to move in a simple straight line, was the loose thread. That was the clue. That was the first whisper that something was hiding in the glare, something massive enough to take hold of a great bright star and pull it, ever so gently, off its course, over and over again, age after age. And there was a man, a careful and brilliant man, who looked at that wobble and would not let it go, who sat with it and thought about it, and slowly came to a conclusion that no one had quite dared to reach before, a conclusion that pointed with quiet confidence straight at something no eye could see. His name was Friedrich Wilhelm Bessel, and his story, the story of how he caught an invisible star by the gentlest wobble of a bright one, is where we'll go next. Friedrich Wilhelm Bessel was not the kind of man who made guesses. He was the kind of man who measured things. Carefully. Patiently. With the sort of quiet stubbornness that is, in science, one of the most useful qualities there is. And by the time he turned his attention to the wobble of Sirius, he had already done something that no human being in all of history had managed to do before him. He had measured the distance to a star. Think about what that means for a moment, and let it settle. For all of recorded human history, for every civilization that ever tilted its head back and watched the night sky with wonder, the stars were simply there. Beautiful, unreachable, mysterious in the most complete sense of that word. Nobody knew how far away they were. Nobody had a reliable way to find out. They might as well have been painted onto the inside of a bowl. And then, in 1838, Friedrich Wilhelm Bessel changed that. He did it with a star called 61 Cygni, a faint, rather unremarkable little star in the constellation Cygnus, the swan. The method he used is called parallax, and it is worth taking a moment to understand it, because it is actually something your own brain does for you every single day without asking permission. Close one eye, look at something close to you, a lamp, a glass of water, your own hand. Now switch eyes, open the closed one, close the open one, and notice how the near object seems to jump slightly against whatever is behind it. That shift, that apparent change in position, is parallax. Your two eyes see from slightly different angles, and that difference lets your brain calculate depth, lets it figure out that the near thing is near and the far thing is far. Bessel used the same idea, but instead of two eyes, he used two positions of the Earth in its orbit around the Sun. In the summer, the Earth is on one side of the Sun. In the winter, 6 months later, it's on the other side, roughly 300 million kilometers away from where it started. And if you measure a relatively nearby star against the distant background of far more remote stars in summer, and then measure it again in winter, a nearby star will appear to have shifted very slightly. The amount of that shift tells you the distance. The problem is that even for the nearest stars, the shift is almost unimaginably small. We're talking about fractions of an arcsecond, a unit of angle so tiny that a full arcsecond is 1/3600th of a single degree. And Bessel was doing this with instruments made of metal and glass in the 19th century by hand, but he did it. He measured the parallax of 61 Cygni and calculated that it was about 10 light-years away. He was remarkably close. The real distance is about 11.4 light-years. That number, that real physical distance in something humans could begin to imagine, was brand new. Stars were no longer just points in a bowl. They were objects at actual calculable distances in actual physical space. And that changed everything. It changed everything because once you know a star's true distance, you can start asking real questions about its real properties. You can figure out how much light it actually emits, how massive it might be, how it moves through space. Bessel had, in other words, opened the door to stars as objects to be understood rather than merely admired. And he did not stop there, because Bessel was also a man who paid extraordinary attention to proper motion. And this is the concept we need to sit with for a little while because it's the key to everything that followed. Proper motion is simply the way a star moves across the sky over time, not the apparent wobble caused by the Earth's orbit, but the actual physical drift of the star through space. All stars are moving. The Sun is moving. The whole galaxy is a slow, churning dance of stars orbiting the galactic center over vast stretches of time. And some stars, the nearby ones, drift noticeably enough across the sky that over years or decades you can actually chart that motion. Bessel was one of the most meticulous observers of proper motion that the world had yet seen. And what he found when he looked at the data for Sirius was something that bothered him. It bothered him the way a slightly crooked picture bothers a person who cannot walk past it without straightening it. Not alarming. Not dramatic. Just wrong. Quietly, persistently, unmistakably wrong. The path of Sirius across the sky was not a straight line it should have been. A lone star drifting through space would trace a clean, straight path against the background of more distant stars, adjusted for the yearly back and forth of parallax. That's the geometry, that's what the simple picture demands. But Sirius was weaving. Its position, measured year after year, deviated from a straight line in a way that repeated, that had a rhythm to it, that curved in one direction and then curved back. A wave, a wobble, a star that refused to walk a straight line. And Bessel, being Bessel, sat with that wobble and asked the obvious question. The only question that really made sense. What could cause a moving object to trace a wave instead of a line? What kind of force would pull a star gently to one side, let it correct, then pull it back again, over and over, in a pattern? There was really only one answer, if you thought about it clearly. Another mass. An unseen companion. something orbiting the bright star, or more precisely, something that Sirius itself was orbiting, the two of them turning slowly around their shared center of gravity, the way two dancers wheel around the space between them. And because the companion was unseen, because no telescope had ever shown a second point of light beside Sirius, that companion must be dark, or at least very faint, something that gave off too little light to be seen while still being massive enough to sway the brightest star in the sky. In 1844, Bessel published his findings. He announced with quiet confidence that Sirius had an unseen companion. He had done the same analysis for another bright star called Procyon in the constellation Canis Minor, the Lesser Dog, and found the same thing there, the same kind of wobble, the same implication of a hidden partner. He called them, in a phrase that is wonderfully evocative if you let yourself feel it, dark stars. Not because they were malevolent, not because they were exotic in any way he could specify, simply because they were there and not visible. Stars that were dark, hidden in the ordinary sky, disclosed only by the way they gently pulled their bright companions out of their expected paths. Think about what Bessel was actually saying. He was saying that gravity could be a telescope, that you did not need to see something to know it was there, that the invisible left traces in the visible if you looked carefully enough, if you measured precisely enough, if you were patient enough to track the slow and subtle dance. It was a kind of forensic astronomy, a reading of clues in the motions of known things to discover the existence of unknown ones. And it would turn out to be one of the most powerful ideas in the history of the science. Every time we detect a planet orbiting a distant star by the wobble it induces in that star's light, every time we infer dark matter by the way it bends the paths of visible galaxies, we are doing something Bessel did with a star and a pencil and a lot of careful measurement in 1844. He also estimated the orbital period. Based on how quickly the wobble was cycling, how long it took for Sirius to swing from one side to the other and back again, he put the orbital period of the invisible companion at roughly half a century. About 50 years, one slow circuit of the hidden partner around the bright one, taking the better part of a human lifetime to complete. He never saw the companion. Friedrich Wilhelm Bessel, the man who told the world it was there, died in 1846, 2 years after his announcement. He spent those last 2 years having mathematically demonstrated the existence of something no living eye had confirmed, and he would not live to see confirmation come. That confirmation would wait. It would wait 18 years from the date of his paper. And when it finally came, it would come in the most pleasantly accidental way that discoveries sometimes do. Alvan Graham Clark was not an astronomer, not primarily. He was a lens maker. He and his father, Alvan Clark, and eventually his brother, ran a company called Alvan Clark & Sons, based in Massachusetts, and they were among the finest makers of telescope lenses in the world, possibly the finest. The refractor telescope, the kind that gathers and focuses light through glass rather than bouncing it off a mirror, depends entirely on the quality of its lens, the purity of the glass, the precision of its grinding and polishing, the absence of bubbles or streaks or irregularities that would blur the image. And the Clarks had a gift for this, a craftsman's feel for glass, developed over years of patient, careful work. They had built lenses for observatories across America, and their reputation had grown until they received a commission that was, for the time, extraordinary. The Dearborn Observatory in Chicago had ordered from them an objective lens, the main gathering lens, of 18.5 inches in diameter. 18.5 inches. At the time, in 1862, this was the largest telescope lens in the United States. The largest. The project had taken years, and now it was finished, and before it could be shipped off to its new home, it needed to be tested. This is standard practice. You grind and polish a lens with the best technique available, but you cannot be fully certain of its quality until you actually point it at the sky and see what it shows you. And so, on the night of January 31st, 1862, Alvan Graham Clark pointed the new 18.5-inch lens at the sky. He chose a bright target, a practical choice, something that would show him quickly if the lens was working as it should. He pointed it at the brightest star in the sky. He pointed it at Sirius, and right beside it, just barely separated from the overwhelming glare of the brilliant blue-white primary, so close and so faint that it was nearly swallowed by the light of its companion, there was another point of light. Small, faint, easily missed. In fact, he thought at first that he was seeing an artifact, a ghost image created by some imperfection in the lens, the kind of false point of light that does appear sometimes when a very bright object is imaged through glass that isn't quite right. But he looked more carefully, and he tracked it, and he saw that it moved with Sirius, that it held its position relative to the bright star as the sky turned, as Sirius drifted, and that it was real. It was not a lens ghost. It was a real point of light in the sky, a faint companion, sitting at almost exactly the angular distance from Sirius that Bessel's calculations had predicted, in almost exactly the direction the math had pointed. Bessel had been dead for 16 years, but his math was right there, quietly correct, having waited 18 years for someone with a good enough instrument to check it. And now someone had, accidentally, while testing a new lens. The companion was given a name almost immediately, one that still carries a certain charm. Sirius is the dog star because it sits in the constellation Canis Major, the greater dog, and has been called the dog star since ancient Greece, since Rome, since probably before anyone was writing names down. And a dog, everyone knows, sometimes has a pup, a puppy. So the faint companion beside the great bright dog star was called, with the kind of quiet affection that sometimes creeps into scientific naming, the pup. Sirius B, formally. The pup, informally. A small, faint, almost invisible little point of light beside its brilliant parent, discovered at last on a winter night in Massachusetts, when a man was simply checking whether his lens worked. It's worth pausing here because there's something beautiful happening in this story, something that gets better the longer you hold it in mind. The gap between 1844 and 1862 is not just a gap in time, it's a gap between knowing something and seeing something. Bessel knew the companion existed. He had reasoned it out with care and precision from the wobble in Sirius's path, and he had committed to that conclusion in print, in a published paper, as clearly as a scientist can commit to anything. He said something is there, something massive, something that takes roughly 50 years to orbit. And he was right, but he could not see it. Nobody could, because no telescope then in existence was quite large enough, quite sharp enough to find that faint point hiding in the overwhelming light of the bright star next to it. Knowing without seeing. Certainty without confirmation. It's a strange place to live in scientifically, and Bessel lived there for the last 2 years of his life. And then, 18 years after his death, a craftsman testing a piece of glass found it. Not because he was looking for it, not because he knew it was there, but because he pointed a good enough instrument at the right star on the right night, and the universe simply showed it to him. The body was exactly where the math had said the body would be. This is one of the things that makes physics, real physics, so extraordinary. The equations, when they're right, don't just describe what you've seen, they point at what you haven't seen yet. They reach ahead of observation into darkness and say, there is something here with this mass at this distance, taking this long to orbit. And then, eventually, if you build something good enough to look, you look, and the something is there. Not because the math was lucky, but because the math was describing something real, something actual, something made of matter and subject to gravity, hiding in the dark beside a bright star, going around and around on its 50-year circuit, utterly indifferent to whether any human eye ever found it or not. It was there before Bessel calculated it. It would have been there if he hadn't. The math didn't conjure it. The math just pointed. Take a moment, if you like, to let that thought settle. The math just pointed. And after 18 years, someone looked where it pointed, and there it was. Now, the question that must have occurred to anyone who heard about the discovery, then and now, is an obvious one. All right, there's a companion. There's a second star beside Sirius, invisible to the naked eye, first seen on January 31st, 1862. But what is it? Not just a label, not just a faint companion or Sirius B as a name. What kind of object is it? What is that little point of light actually doing there, and why is it so faint? And why does it have enough mass to wobble the brightest star in the sky and yet be too dim to be seen without one of the finest telescopes then available? The answer to those questions would take a great deal longer to arrive than the initial sighting did. And when it arrived, it would be stranger than anything Bessel or Clarke had imagined. Because what Clarke had found beside Sirius was not a small, quiet, unremarkable secondary star, the way many binary companions are. It was something that, once understood, turned out to be one of the most astonishing objects that nature produces. Something that shouldn't exist and does. Something that the physics of the 19th century literally had no framework to explain, but in 1862 they didn't know that yet. In 1862, the pup was simply a faint companion to a bright star, a confirmation of a dead man's prediction, a pleasant vindication of Bessel's careful work. And for a while, the story seemed to end there. Found, catalogued, the companion of Sirius, fainter than the primary, sitting at roughly the distance and direction the math had pointed to. Mystery solved, more or less, or so it seemed. What nobody realized yet was that finding the pup was not the end of the mystery. It was the beginning of a deeper and stranger one. Because as the years passed and astronomers tried to understand exactly what they were looking at, the numbers didn't quite make sense. The mass implied by the wobble, the mass that Bessel's analysis demanded, was substantial, not a tiny, wispy thing, a real, significant stellar mass. And yet the light coming from that companion was dim, very dim, much dimmer than it should be for an object that massive. Stars, as a rule, the more massive they are, the brighter they are. It's almost a law of stellar society. Mass and brightness travel together. More mass means more gravity, more pressure in the core, more fusion, more light. That's the bargain a normal star strikes. But the pup wasn't playing by those rules. The pup was heavy, at least gravitationally, in terms of what it was doing to Sirius. But it was faint, obstinately, impossibly faint, for its implied mass. And when astronomers eventually managed to measure its spectrum, to spread its light out and read the message it was carrying about the temperature of its surface, the contradiction got even worse. Its spectrum showed that it was hot. Not just warm, not just pleasantly glowing. Hot, intensely, ferociously hot, far hotter than the surface of the sun. And yet it was dim, dim for its mass, dim for its temperature. An object that was supposed to be bright on two separate grounds, mass and temperature, and was failing on both counts to show up the way it should. Somewhere between too massive to be faint and too hot to be dim, the pup sat there in the sky, politely defying the rules, waiting for the physics to catch up with it. It would wait until the 20th century for that. Until a new framework for understanding matter arrived, one built not from the comfortable mechanical intuitions of classical physics, but from the strange and counterintuitive world of quantum mechanics. And when that framework arrived, what it revealed about the pup, about what the pup actually was, and what it was actually made of and what was holding it together, turned out to be one of the most genuinely startling things that the study of stars has ever uncovered. But before we can understand that, before we can really feel the full weight of what Clarke found beside Sirius on that January night, we need to understand what a dying star does. We need to follow the life, or rather the end of a life, that produced the pup in the first place. And that story, the story of how a star dies, how it collapses and blazes and sheds its outer skin and leaves behind this impossible dense remnant, is the story we'll begin to move into next, because the pup is a product of a death. And understanding the death is what lets you understand the corpse. So stay with us, settle in wherever you are. The physics of what that little faint point of light actually is, and why it should not, by any ordinary understanding, be able to exist, is waiting just ahead, and it is extraordinary. But for now, for just a moment, let yourself sit with the simpler, more human part of what we've found. Bessel in 1844 measuring a wobble, Clarke in 1862 testing a lens, a dead man's prediction sitting quietly correct for 18 years, waiting for the glass to be good enough. And finally, on a winter night in Massachusetts, the faint little pup, blinking into view right where the math said it would be. Not conjured, not guessed, not stumbled upon by luck alone, found. By the fingerprint it left on the motion of its brilliant companion, by the slow and patient logic of gravity, by a physicist who trusted the numbers even when the sky showed nothing. That is what Bessel did. He taught the universe a way to give itself away. And the thing it revealed, that tiny, faint point of light that put beside the dog star, is so strange, so deeply improbable in its very existence, that even now, knowing what we know, it is hard to fully accept that something like it is real. That the brightest point in the night sky is sharing its light with an object like that. An object that we'll spend the next part of this quiet night understanding. For now, close your eyes if you like. Think of Sirius up there, brilliant and steady, the brightest star in the sky, and just beside it, invisible to your naked eye, lost in the glare, the pup, patient, ancient, incredibly dense, and waiting to be understood. We'll get there, slowly, together. So let's go back a little before the pup was found, before Clarke pressed his eye to that cold eyepiece on a Massachusetts winter night. Let's go back to where the detective story really begins. Not in 1862, but in 1838, and not with Sirius at all. Friedrich Wilhelm Bessel was, by any reasonable measure, one of the most careful men in the history of astronomy. Not dramatic, not famous in the way that Newton or Galileo became famous, but careful, precise, the kind of scientist who understood that the truth about the sky was embedded in small numbers, in tiny discrepancies, in measurements that most people wouldn't bother making because the differences seemed too slight to matter. In 1838, Bessel turned that precision toward a problem that had frustrated astronomers for centuries. How far away are the stars? You might think that's an odd thing not to know. They're up there after all. You can see them. But seeing something and knowing its distance are very different things, and for most of human history, the stars existed at an unspecified, essentially infinite remove. Ancient astronomers knew they were far. They didn't know how far. And without that number, without actual distance, everything else about a star was just description. Brightness, color, position, a catalogue of appearances with no depth beneath them. Bessel wanted the depth. The method he used is called parallax, and it is, at its heart, a beautifully simple idea. Hold your finger in front of your face and close one eye, then the other. Watch your finger seem to jump against the background. It hasn't moved. You have. And the amount it seems to jump depends on how far away it is. Close fingers jump more, distant ones jump less. If you know the distance between your two eyes and you measure the angle of the jump, you can calculate exactly how far away the finger is. It's geometry. Pure, old, unargued geometry. Now do that with a star. Instead of your two eyes, use two positions of the Earth in its orbit around the Sun. One in January, one in July, when we're on opposite sides. A nearby star, seen against the backdrop of much more distant ones, should appear to shift very slightly as the Earth swings from one side of its orbit to the other. The shift will be tiny, almost nothing, but it will be there, and it will be real, and it will tell you the distance. The difficulty is that the shift is astonishingly small. Even for the nearest stars, it amounts to less than a single arc second, less than 1/3600th of a degree. It is a measurement that demands extraordinary patience and extraordinary instruments and an almost ruthless willingness to question your own result. Many astronomers before Bessel had tried. None had succeeded convincingly. Bessel chose a star called 61 Cygni. It sits in the constellation Cygnus the Swan, and he chose it not because it was particularly bright or dramatic, but because it had a large proper motion, meaning it moved noticeably against the background stars over time, which suggested it was probably nearby. If it were moving that fast across the sky, from our perspective, it was almost certainly not buried deep in the galaxy. It was probably a neighbor. He was right. After 18 months of careful, systematic measurement, Bessel announced in 1838 that he had measured the parallax of 61 Cygni. The star was about 10 light years away, give or take, the first real distance to another sun. For the first time in human history, the word far had a number attached to it when we talked about the stars, not metaphorically far, measurably, geometrically, genuinely 10 light years far. It was a landmark in astronomy. And it established something else just as important as the distance itself. It established Bessel's method. It proved that the sky could be read with numbers, that patience and precision could pull real physical facts out of apparent emptiness. And so when, just a few years later, Bessel turned his attention to Sirius and started noticing something odd about the way it moved, he had the credibility and the tools to take that oddness seriously. Here's what he noticed. Stars move, not the daily wheeling of the sky caused by Earth's rotation, and not the slower yearly drift caused by Earth's orbit. Something different, a genuine, real motion across the sky, building up over years and decades and centuries as stars travel through the galaxy on their own paths. This is called proper motion, and for Sirius, it is quite noticeable. Sirius is close enough to us and moving at enough of a clip through space that it crawls visibly across the background of more distant stars over the span of human lifetimes. Bessel had historical records of where Sirius had been, careful measurements stretching back decades, and when he plotted them, when he traced the path Sirius had walked across the sky, it wasn't straight. It should have been straight. A star moving through empty space on a constant trajectory with no forces acting on it should trace a clean, straight line across the background sky as we watch it from Earth. That's just simple geometry. Something moving in one direction keeps moving in that direction. Sirius was not doing that. Its path was wavy, not dramatically, extravagantly wavy, but wavy nonetheless in a slow, regular, undulating pattern that repeated with a period of roughly half a century. And Bessel knew what a periodic, regular wobble meant. It meant something was pulling. Something with mass, orbiting the same center of gravity, tugging the visible star first one way and then the other in a great, slow waltz. He couldn't see the companion. Nobody could. The sky at that point was empty beside Sirius to even the best telescopes of the day. But the motion of Sirius was drawing a picture in the air, a record of a gravitational conversation between two bodies, and Bessel was reading it. He published his findings in 1844. He stated plainly that the proper motions of both Sirius and another bright star, Procyon, could not be reconciled with any known cause except the presence of unseen massive companions. He estimated the orbital period of whatever was accompanying Sirius at around half a century. He called them, in language that carries its own haunting quality across nearly 2 centuries, dark stars, invisible companions, objects massive enough to pull the sky's most brilliant star into a waltz, but dark, utterly dark, giving off no light that any telescope of the time could capture. Bessel did not live to see confirmation. He died in 1846, 2 years after his announcement, without ever knowing whether the dark star beside Sirius was real or a mathematical ghost, an artifact of error, a wrong interpretation of imperfect data. He trusted the numbers. He published the conclusion. And then he was gone. The dark star waited. 18 years passed. Telescopes improved. The question stayed open, occasionally revisited, never resolved. You couldn't see anything there. But the wobble persisted. Later, astronomers refining Bessel's work kept arriving at the same uncomfortable conclusion. Something was there. Something with real mass, pulling a real star, generation after generation of careful measurement confirming what the eye refused to show. And then on the evening of January 31st, 1862, a young American named Alvan Graham Clark sat down at a telescope he was not supposed to be looking at stars through yet. The telescope in question was an 18.5-inch refractor built by his father's firm, Alvan Clark and Sons, in Cambridgeport, Massachusetts. At the time, it was the largest refracting telescope in the United States, possibly in the world, and it had been commissioned by a university in Mississippi, though the outbreak of the Civil War would ultimately complicate that arrangement considerably. But in January 1862, the lens had been ground and assembled and was awaiting delivery, and the Clark workshop needed to test it. Testing a great lens is not a casual affair. The quality of a refractor, the sharpness and clarity of the images it produces, depends on the precision of the glass, and that precision has to be verified against the actual sky. You point it at a bright star, and you look at how perfectly the light comes to focus, how clean and sharp the point is, whether there are halos or distortions or smearing that would indicate imperfections in the grinding. You use bright stars because you need a strong source of light, and the brightest star in the night sky in January 1862 above Cambridgeport, Massachusetts, was Sirius, so Alvan Graham Clark pointed the new lens at Sirius. What he saw almost immediately was a faint companion, a tiny, faint, distinct point of light very close to Sirius, half drowned in the blazing glare of the primary star, but unmistakably there, real. A separate source of light at a specific position, a specific separation, a specific angle. He was not looking for it. He was testing glass, but there it was. The position was checked, the calculations were run, and what emerged from those calculations was the confirmation that the astronomical community had half believed and half doubted for 18 years. The faint companion's position matched, as well as the measurements could verify, exactly the location that Bessel's predicted orbital motion required it to be. The dark star was not dark after all. It was simply faint, overwhelmed by its companion, lost in the glare, waiting for a good enough piece of glass turned the right direction on the right night. They called it the pup, a small, slightly playful name for the small companion to Sirius, the dog star. The pup beside the dog. It's worth pausing here, in the stillness of wherever you are listening, to appreciate the shape of what just happened across those 18 years. A man in 1844 looked at a wobble in the motion of a star and said, "Something is there, something with mass, something invisible, something that will not be found until the instruments are better and the patience holds." He calculated as best he could how long its orbit must take. He named it, gently and precisely, a dark star. And then, 18 years later, on a night when someone was testing a lens, by a kind of beautiful accident layered on top of decades of prediction, the dark star blinked into view. Right there, where the math had said. Gravity had given it away, not light. Gravity. The oldest force, the most patient force, the one that works across any distance and leaves its marks in the motions of visible things. Bessel had understood before most astronomers were ready to understand it that you do not need to see a thing to know it is there. You only need to read what it does to the things you can see. That is a profound idea, and it didn't end with Sirius. The same method, gravity as an invisible detector, would eventually be used to find planets around distant stars, to infer the existence of black holes at the centers of galaxies, to map the dark matter that fills the universe with mass we cannot directly observe. It all traces in some sense back to the logic Bessel used when he looked at Sirius's wavy path and said, "Something is pulling it, something is there." But what is there exactly? That faint little pup right there beside the dog star. What, when you actually look closely, when you actually ask the physics, is it made of? The answer turns out to be the truly strange part of this story. Because the pup is not just a dim star, it is not simply a small, cool, ordinary star that happens to be faint. It is something far more radical than that. Something that should not, by the physics that governed the universe as scientists understood it in 1862, be possible at all. So, let's talk about what it actually is. The pup, that faint little point that Alvan Graham Clark picked out beside the blazing dog star on the last night of January 1862, is a white dwarf. That is the name it was eventually given, and the name is honest in one way. It is white, or rather a brilliant blue-white. But it is quietly deceptive in another, because the word dwarf suggests something small and therefore insignificant, something minor, a footnote beside its brilliant companion. And that is exactly wrong. The pup is the most astonishing object in this part of the galaxy. Its smallness is precisely what makes it extraordinary. Here is the number that changes everything, and I want you to sit with it for a moment, even if you're already halfway to sleep. The mass of the sun. All of it. All that fire and pressure and enormity, all those hundreds of thousands of times the mass of the Earth, all the weight that produces enough gravity to hold 8 planets in their orbits at distances of billions of kilometers, all of that mass, give or take a small fraction, is packed inside Sirius B, inside the pup. And Sirius B has a radius of roughly 5,800 kilometers, slightly smaller than the Earth. This is not a rounding error. This is not an approximation that might be off by a large factor. This is, as precisely as modern instruments can determine, what the pup is: a sun's worth of matter compressed into a ball you could fit inside our own planet's sphere. Let me try to make that feel real, because numbers at this scale have a way of sliding past the mind without quite landing. Imagine you have a sugar cube, one of those small white ones you might drop into a cup of tea on a cold night. Pick it up, feel the weight of it. Practically nothing, isn't it? A few grams. Now imagine that same sugar cube is made of the material from inside Sirius B. That cube would weigh something in the range of several tons. A small family car weighs roughly a ton. Your sugar cube of dead star would weigh as much as several cars stacked together. The material is not just dense in the way that lead is denser than wood, it is dense in a way that has no counterpart in anything you have ever touched, anything you will ever touch, anything that could exist on the surface of a world like ours. And a teaspoon, a proper kitchen teaspoon full of material from Sirius B, set it on a scale, that teaspoon would register a weight of multiple tons, several tons. The spoon itself would be structurally irrelevant, a smear of ordinary metal atoms against the incomprehensible pressure of what it contained. The scale would be destroyed. The table beneath it would be destroyed. The material would fall instantly through whatever ordinary matter you tried to rest it on, because the forces holding ordinary matter in its familiar shapes, the electromagnetic repulsion between electron shells, would be completely inadequate to resist the weight. This is what Alvin Graham Clark's tiny point of light actually is. This is what Bessel's dark star turned out to be. Not a dim companion, but a graveyard of impossible density, sitting quietly in the dark beside one of the brightest and most beautifully ordinary-seeming stars in the sky. Now, you might reasonably ask, and if you're still awake enough to ask it, it's a good question. How? How does something with that much mass end up that small? And perhaps more urgently, if it has that much mass, if its own gravity is pressing inward with that kind of force, what is holding it up? Ordinary stars are held up by the pressure of the nuclear fire burning inside them. Outward push of heat and radiation against the inward pull of gravity. A balance held for millions or billions of years. But Sirius B is not burning, it is not fusing hydrogen, it has no active nuclear fuel left. The fire has gone out. So what, precisely, is stopping it from collapsing further? What is holding a sun's worth of gravity at bay? The answer, when it finally came, arrived not from astronomy but from the newly born science of quantum mechanics in 1926. And the man who worked it out was a British physicist named Ralph H. Fowler. To understand what Fowler understood, we have to step into the interior of a white dwarf for a moment. Not the surface, which we'll come back to, but the interior. Down into the material itself, into the physics of what that matter is doing. In an ordinary star, in the Sun, for instance, or in the star that Sirius B used to be, atoms exist at such high temperatures that they're completely ionized. What that means is that the electrons have been stripped away from their parent nuclei, so you have a soup, a dense, hot, furious soup of bare atomic nuclei, mostly carbon and oxygen in the case of a typical white dwarf, and a sea of free electrons swarming around them. In an ordinary star, the electrons and nuclei are all moving at speeds governed by the temperature. Hot means fast. The pressure this generates, thermal pressure, is what pushes back against gravity. But in a white dwarf, the temperature has dropped low enough and the density has risen high enough that something different takes over. The electrons, which are fermions, a particular category of quantum particle, come under the governance of a rule that has no classical equivalent, no analogue in the physics of the large-scale world. This rule was formulated by the Austrian physicist Wolfgang Pauli in 1925, and it is called the Pauli exclusion principle. The principle, stated simply, is this: no two electrons can occupy the same quantum state at the same time. Each electron must have a unique combination of quantum properties: position, momentum, spin. You cannot stack two electrons on top of each other, so to speak. They refuse. The universe will not allow it. In most circumstances, in the electron clouds of ordinary atoms, or in the comparatively thin plasma of a normal stellar interior, this principle operates quietly in the background. There is enough space, enough room in quantum terms, that electrons find their distinct states without crowding. But squeeze the matter hard enough, compress a stellar core to the density we're describing, millions of grams per cubic centimeter, and suddenly the electrons have nowhere to go. The lowest quantum states are all filled. The only way to add more compression would be to force electrons into states that are already occupied, and the universe says no. This resistance, this quantum stubbornness, is called electron degeneracy pressure. And here is the remarkable thing about it: it does not depend on temperature. In ordinary thermal pressure, if a gas cools, it contracts. Pressure falls with temperature. But electron degeneracy pressure is not thermal. It is not generated by heat or motion in the conventional sense. It is generated purely by the quantum mechanical fact of particles that must be distinguishable from each other, that cannot share a state. You could, in principle, cool a white dwarf to absolute zero, the coldest possible temperature, and the electron degeneracy pressure would remain. It is, in a deep sense, a pressure maintained by a law of nature rather than by energy. This is what Fowler worked out in 1926 using the tools that quantum mechanics had only just provided. He showed that a sufficiently compressed stellar remnant would be held up not by fire, but by this quantum rule. Not by what the star is doing, but by what the electrons in their deep quantum nature simply cannot stop doing, which is refusing to be identical to one another. It is a strange thing to think about on a quiet night. The brightest star in our sky has a companion held together by a law of quantum mechanics, by a principle that says the universe does not permit particles to be indistinguishable. That subtle, abstract rule, which also underlies the structure of every atom, the behavior of every electron in the computer, the phone, the lamp near your bed, is what prevents Sirius B from collapsing into something far more violent. A rule about the identity of electrons is the only thing standing between that dead star and complete annihilation. Fowler gave the world the mechanism. He showed that degenerate stars were stable, but he did not immediately ask or answer the question that was lurking in his own mathematics, because the electron degeneracy pressure, this quantum law, has limits. It can hold up a dead star, yes, but only up to a certain mass. If you add too much matter to a white dwarf, the electrons, forced into higher and higher energy states by the exclusion principle, eventually begin to move at speeds approaching the speed of light. And at those speeds, relativistic effects kick in, and the math changes, and the pressure, although still present, no longer increases fast enough to hold against the increasing gravity. There is a ceiling. But we are getting ahead of ourselves. We will come back to the ceiling, because first there is the surface of Sirius B to visit, and the surface tells its own astonishing story. The pup, despite being cold by stellar standards, cold in the sense that it has no fuel left and is slowly losing heat, is right now extraordinarily hot. Its surface temperature is approximately 25,000 Kelvin, 25,000. The Sun's surface is roughly 5,800 Kelvin. Sirius B's surface is more than 4 times hotter than the Sun's. This seems paradoxical, doesn't it? We've been saying it's a stellar corpse, a dead thing cooling in the dark, and yet its surface runs at 4 times the solar temperature. The resolution of this paradox lies in where that heat is coming from and how long it lasts. When a star sheds its outer layers and becomes a white dwarf, the exposed core is the remnant of a stellar interior that spent millions of years at temperatures of many millions of degrees. The material retains that stored heat. And in a white dwarf, without the constant fusion reactions replenishing energy, the star is simply radiating away what it accumulated. It is a coal that has been taken off the fire. On a human timescale, on even a civilizational timescale, it seems permanent and stable and hot. But on the scale of billions of years, it is cooling. Slowly, steadily, it will dim and fade and eventually become what is called a black dwarf, a cold, dark cinder that emits almost no light. The universe is not old enough yet for any black dwarfs to exist. They are a fate that lies ahead, deep in time, not yet arrived. But right now, Sirius B is still very hot at its surface, 25,000 Kelvin hot, which raises an obvious question. If it's that hot, why can you not see it without a telescope? Why did it stay invisible for 18 years after Bessel predicted it? The answer has 2 parts, and both of them matter. The first part is about size, a star's luminosity, total light output, and depends both on its temperature and on its surface area. A hotter surface radiates more energy per square meter, but if the total surface is small enough, the total output can still be modest. And Sirius B, with its radius of roughly 5,800 kilometers, has a surface area that is tiny compared to even the modest Sun. The Sun has a radius of about 695,000 kilometers. Sirius B's radius is less than 1% of that. Surface area scales with the square of the radius, so Sirius B's surface area is roughly less than 1/10,000th of the Sun's, even with a temperature 4 times higher, which, yes, produces more energy per square meter. The total light output is far, far less than what you'd expect from something that hot if it were large. The result is that Sirius B puts out roughly 4 to 5% of the Sun's luminosity, genuinely faint for all its blazing surface temperature. The second part of the answer is that it has an extraordinarily bright neighbor. Sirius A outshines Sirius B in visible light by a factor of roughly 10,000 to 1. That is the contrast you are trying to see past. In practice, when you look at Sirius in the night sky, the brilliant, dazzling blue-white point of light you see is essentially entirely Sirius A. The pup is there, 35 or 40 or 50 arcseconds away, depending on where in its 50-year orbit it sits at a given moment. But it is completely drowned, swamped, erased. The glare of the primary smears across the eyepiece of a telescope and buries the companion in a wash of scattered light. This is why Sirius B was only ever going to be detected when the orbital geometry was favorable, when the two stars were near the wider parts of their orbit, giving maximum angular separation, and when the observer had a superb instrument, and when the atmospheric seeing was good, and when all of these conditions happened to coincide. Alvan Graham Clark, on the night of January 31st, 1862, had all of those things. The gap was wide enough. The 5-inch refractor was the finest in the United States. And the sky cooperated. The pup blinked into view. Tonight, or on any clear night, you can point a moderately powerful amateur telescope at Sirius and, depending on the year and the state of the orbit, catch a glimpse of that faint companion. It moves year by year around the brilliant primary. It is always the same distance the math predicts. It is always the mass the equations require. It is always exactly what Bessel's wobble said must be there. And what is it like if you tried to imagine standing on its surface? Purely as an exercise, since no structure made of ordinary matter could exist there, the surface gravity of Sirius B is on the order of 100,000 to 200,000 times the surface gravity of Earth. Your body, if transplanted there, a thought experiment only, it would be instantly lethal in any number of ways, would press down with a weight of something like 200,000 to 300,000 times your Earth weight. If you weighed 70 kilograms on Earth, you would weigh something in the range of several million kilograms on the surface of Sirius B. The word crushing is not hyperbole, it is precise. Every atom of ordinary matter that landed on that surface would be immediately flattened, reorganized, incorporated into the degenerate structure below. Nothing falls softly onto a white dwarf. Nothing that arrives there retains its original form. Material from the outer layers of a companion star, if a binary system's geometry is right, sometimes spirals down onto a white dwarf surface. When it does, it arrives at tremendous velocity, compressed and heated in ways that produce some of the brightest thermonuclear explosions in the galaxy. Events we call novae, or in more extreme cases, type Ia supernovae. But that is for a different night. For now, simply rest with the picture. That brilliant, beautiful, ancient point of light that every human culture has watched in the sky. The star that signaled the Nile's flooding to the Egyptians. The star that told the Greeks that summer's hottest days had arrived. the star that woke the attention of Friedrich Bessel when its path refused to stay straight, has sitting beside it in the dark a ball of quantum-imprisoned matter the size of our planet, with the mass of our Sun, a surface running at 4 times the solar temperature, and gravity that would reduce any ordinary structure to nothing in less than a moment. And for all of that, you cannot see it without a good telescope. It is there, and it is extraordinary, and it is almost entirely hidden by the brilliance of its companion. There is something quietly poetic about that, I think. The dead outweighing the living, in mass, in density, in the sheer physics of what it has become, and yet completely invisible behind the living star's light. The corpse concealed by the brightness of the one it left behind. The glare of Sirius A is not just a nuisance to observers, it is, in a sense, the reason this whole story has the shape it does. If the 2 stars were comparable in brightness, the companion would have been obvious to telescopes centuries ago, and there would be no detective story, no wobble noticed in Bessel's data, no 18-year wait. The very concealment is what made the prediction story possible. If the pup were easy to see, nobody would have had occasion to be astonished that it was found on paper first. But the companion is faint, swamped, hidden in the glare. And so the only way the 19th century had to detect it was through what it does rather than what it looks like. And what it does is tug, steadily, patiently, with a mass nearly equal to the Sun's across a separation that ranges over the 50-year orbit from as close as 8 astronomical units to as far as 31.5 astronomical units, tugging at Sirius A in a rhythm that is encoded in the tiny, sideways shift of the primary's path across the sky. That is the wobble Bessel saw. That is the record the invisible star wrote in the sky, in the only language available to it, the language of gravity, the motion of its partner, the subtle bending of a path that should have been straight. Now, there is one more piece of the physics that I want to stay with before we move forward. Because we've established that Sirius B is held up by electron degeneracy pressure, by this quantum law that prevents electrons from sharing states, by Fowler's 1926 insight. But the question that Fowler's work naturally raised, and that a young Indian physicist would answer with startling and initially controversial clarity in the early 1930s, is this. If electron degeneracy pressure is what holds a white dwarf up, does that pressure have a limit? Is there a mass above which even quantum stubbornness cannot hold the star together? The answer, as you may already sense, is yes, there is a limit, and the man who calculated it was Subrahmanyan Chandrasekhar. Chandrasekhar was 19 years old, travelling by ship from India to England in 1930 on his way to Cambridge to the world of British astrophysics. When he did the calculation, he was working out during the voyage what happened when you applied Fowler's degenerate matter physics rigorously, including the relativistic corrections for electrons moving at speeds approaching the speed of light. And what he found was that the degeneracy pressure, when electrons are forced to move relativistically, does not increase fast enough to stop collapse if the mass of the white dwarf exceeds a certain value. That value, the maximum mass a white dwarf can have, works out to approximately 1.4 times the mass of the Sun. 1.4 solar masses. Cross that threshold, and the electron degeneracy pressure is insufficient. The star collapses further. What it collapses to is a different subject, a subject for other dark nights. But the threshold matters, and Sirius B sits close enough to it that the relationship is not comfortable. Sirius B has a mass of approximately 1 solar mass, 1.0, close to 1.02 by some careful measurements. The Chandrasekhar limit is 1.4, so there is a gap, a margin of roughly 0.4 solar masses between what Sirius B is and what would send it past the point of no return. That sounds like a comfortable margin, and in normal circumstances it is. Sirius B is not about to exceed the Chandrasekhar limit by itself. But there are circumstances and again, this is for a different night, in which white dwarfs in binary systems can accrete matter from companions, slowly accumulating mass, approaching that limit over time. The universe keeps notes on these things. Chandrasekhar presented his result in 1935 at a meeting of the Royal Astronomical Society in London, and the response was not warmly welcoming. Arthur Eddington, then one of the most distinguished astrophysicists in the world, the man who had led the 1919 expedition that confirmed Einstein's general relativity, publicly dismissed Chandrasekhar's calculation. Eddington insisted wrongly that nature would not permit stars to collapse in this way, that the result was physically absurd, that something must be wrong with the mathematics. It was not a minor academic disagreement. It was, for a while, a real setback for Chandrasekhar's career and for the acceptance of his result. But the mathematics was correct, the physics was right. Eventually, the astronomical community came around, and in 1983, Subramanian Chandrasekhar received the Nobel Prize in Physics, partly for this work, for the calculation he had done as a 19-year-old on a ship, a calculation that told the universe what its dead stars were and were not permitted to weigh. And speaking of weight and of gravity, there is one more extraordinary property of Sirius B that connects the dead star not just to quantum mechanics, but to Einstein's general relativity. And this one is quiet and subtle and beautiful. When light climbs out of a gravitational field, it loses energy. This is a prediction of general relativity. In everyday life, near weak gravitational sources like the Earth, this effect is almost unmeasurably small. It exists, and we do measure it, and we have to account for it in GPS satellites, but it's tiny. But near something with Sirius B's ferocious surface gravity, 100,000 or more times Earth's, the effect is substantial enough to measure with spectra. When Sirius B emits light from its surface, that light has to climb out of an extraordinarily deep gravitational well. To do so, it loses energy. And light that loses energy shifts toward the red end of the spectrum, longer wavelengths, lower frequency, redder color. This is gravitational redshift. And if you know the mass and the radius of the object the light is climbing away from, you can calculate exactly how much redshift to expect. Then you can observe Sirius B's spectrum and see if the measured shift matches the prediction. A first attempt was made by Walter Sidney Adams in 1925, before Fowler had even worked out the quantum mechanics of degenerate matter, which is a measure of how fast the observational and theoretical sides were moving in parallel during those years. Adams tried to measure the gravitational redshift of Sirius B's light. The technical difficulties were severe. The glare of Sirius A contaminated the spectrum, making it hard to isolate B's light cleanly. His measurements suggested a redshift broadly consistent with a dense, compact object, but it was not precise. The really clean confirmation had to wait until the Hubble Space Telescope. In 2005, astronomers used Hubble to take spectra of Sirius B at a time when the two stars were well separated in the orbit, reducing the contamination from A's glare. The measured gravitational redshift matched the prediction from general relativity, matched the value you'd calculate knowing Sirius B's mass and its Earth-sized radius, to a precision that left no serious doubt. A dead star 8.5 light-years away, in our own immediate neighborhood of the galaxy, was confirming Einstein. The light leaving that tiny, dense, quantum-held ball was stretched by gravity exactly as the equations of general relativity said it should be. There are moments in science where several enormous ideas converge on a single object. Sirius B is one of those moments. The mass of a sun held in an Earth-sized volume, held together by a quantum law discovered in the 1920s, proving a prediction from Einstein's gravity measured by a space telescope launched in 1990, circling a star whose invisible wobble was noticed by a German astronomer in 1844, confirmed by a lensmaker's son in 1862. All of that converges on that quiet, faint, extraordinary point of light sitting beside the dog star. And still, on most nights, you cannot see it without a good telescope. You look up at Sirius and you see one blazing ice-white point, and you have no particular reason to suspect that anything else is there. The brightness of Sirius A, absolute visual magnitude around 1.4, apparent magnitude minus 1.46, roughly twice as bright as Canopus, the next brightest star, drowns everything near it. Drowns the pup completely in the casual glance. The contrast, 10,000 to 1 in visible light, is worth pausing over one more time because it tells you something about what the human eye was designed by evolution, by millions of years of survival on an ordinary world, to perceive. We are built to notice what is brightest. We are built to attend to what our senses can directly register. And what is directly in front of us, blazing, is Sirius A. What is hidden beside it, crushed and dense and quantum strange, is invisible without instruments. And that invisibility, as Bessel's story teaches us, is not the end of the matter. What we cannot see, gravity can still betray. The universe keeps its own notes in the motions of visible things, in the tiny deviations from straight lines, in the wavy paths that patient astronomers track across decades. The dark companion leaves its signature whether we can see it or not. It tucks into Sirius A's path like a handwriting across the sky. Something is here. Now, there is one thing I want to say clearly before we go further, because the story of Sirius B has attracted over the years a certain layer of mythology, of claimed mystery, that is worth setting down gently and carefully. Not because mystery is bad. We have been swimming in real mystery all night, and there is more ahead. But because the real story is remarkable enough that it deserves to stand on its own without the false additions. There is a question that sometimes surfaces in books and articles about Sirius, and it runs something like this. How could anyone have known before modern astronomy that Sirius had an invisible companion? And the question sometimes arrives paired with an answer that points to the Dogon people of Mali in West Africa. The claim, popularized in a 1976 book by a writer named Robert Temple called The Sirius Mystery, is that the Dogon possessed knowledge, apparently ancient, apparently traditional, of the existence of an invisible, small, dense companion to Sirius. A companion they called, in some accounts, a very heavy star. This is a fascinating sounding claim, and it attracted enormous attention, but the evidence for it, when examined carefully, does not hold. What actually appears to have happened is this. In the 1930s, French anthropologists Marcel Griaule and Germaine Dieterlen conducted fieldwork among the Dogon. Some of their informants, in conversations about cosmology and traditional knowledge, mentioned things that seemed to overlap with modern astronomical facts about Sirius. Temple, decades later, read these ethnographic reports and constructed the claim that the Dogon must have had access to ancient, perhaps extraterrestrial, knowledge of Sirius B. But there are several problems. The anthropological methods of Griaule and Dieterlen were, by modern standards, flawed in ways that make it difficult to be certain what Dogon people actually traditionally believed versus what they might have absorbed from contact with educated Europeans. European and American astronomers had published widely about Sirius B since the 1860s. Missionaries, travelers, and colonial administrators moved through the region throughout the 19th and early 20th centuries. The idea that Dogon informants in the 1930s might have encountered and incorporated astronomical information from European visitors is not remotely far-fetched. Later, anthropologists who worked with the Dogon found far less evidence of specific astronomical knowledge about Sirius than Griol had claimed. The Sirius mystery turns out, on close inspection, not to be a mystery at all, or rather, to be a much more mundane and much more human mystery. The question of how information travels between cultures, how ethnographic methods can introduce biases, and how ancient mysteries literature tends to find the answer it is looking for. It is worth knowing the claim exists because you may encounter it, but it is not evidence of ancient knowledge, and it does not stand up. The real story, the wobble, the calculation, the 18-year wait, the accidental night of discovery with a new lens, is extraordinary enough. It needs no embroidery. And there is one other myth, a different kind entirely, that floats around the history of Sirius. It is an older one and in some ways more intriguing because it involves some genuinely puzzling historical observations. The puzzle is this: certain ancient writers, among them the Greco-Egyptian astronomer Ptolemy, the Roman writer Seneca, and some classical Chinese observers, describe Sirius as reddish in color. They seem to be saying that the dog star was red or ruddy, and today Sirius is a brilliant blue-white. It is one of the bluest-looking stars in the night sky. It is emphatically not red. If you know that Sirius B was once long ago a red giant, a vast, cool, reddened star puffed out to enormous size before its death, you might wonder, could these ancient observers have been watching a genuinely different Sirius? Could they have been watching, 2,000 years ago, a system in which the companion was still in its red giant phase, still large and bright and red, painting the whole system with a ruddy light? It is a romantic idea, but the timescales make it physically impossible. The red giant phase of what became Sirius B ended roughly 120 million years ago. Human civilization is at most a few tens of thousands of years old. The gap is so enormous, more than 100 million years, that no human observer in antiquity could possibly have witnessed the red giant. The stars we see in historical records are, in this sense, essentially the same stars we see now. So what explains the red Sirius references? Astronomers and historians have worked on this, and the most persuasive explanations are mundane. Sirius, like any star near the horizon, is strongly reddened by the thickness of the atmosphere it shines through. A red Sirius, observed rising or setting, is a perfectly ordinary observation. Ancient descriptions of stellar color are also subject to translation errors, transcription errors, and the general difficulty of mapping ancient color vocabulary onto the precise modern concept of a star's spectral class. Some references that appear to call Sirius red may have been describing the effect of its scintillation, its famous twinkling and color flashing as its light breaks up through turbulent air, rather than its intrinsic color. And in a few cases, it is possible that ancient observers were describing stars other than Sirius, with the identification made uncertain by time and translation. The red Sirius question is a genuine puzzle in the history of astronomy, but it is not evidence that humans watched Sirius B die. That death happened before we existed, before any primate looked up at the sky with the cognitive capacity to notice what color the bright star was. Human beings are, cosmically speaking, very new. The system of Sirius is thought to be roughly 230 to 250 million years old. We are looking at something that was ancient long before our kind arrived, and yet we figured it out. We noticed the wobble. We did the maths. We held the prediction for 18 years and then, on one cold winter night in 1862, confirmed it. We understood the quantum mechanics of what it is made of. We used Einstein's equations to measure its gravity from 8.5 light years away. We sent a telescope into orbit to read the redshift of its light. We are very new and we are very small, and the things we have worked out about a faint star sitting beside a brilliant one in the constellation of the Greater Dog are, when you sit quietly with them, Genuinely astonishing. There is one last piece of the picture I want to settle into before we move toward the end of this night's journey. And it is about the two stars together, the pair dancing around each other in the dark. The orbit of Sirius A and Sirius B around their common center of mass takes approximately 50.1 years to complete, 50 years, give or take a month. So in a human lifetime, you might see just one or two complete orbits. The two stars sweep around each other in an ellipse, not a circle, but a stretched oval, with an eccentricity of about 0.59. What that eccentricity means in plain terms is that the orbit is quite elongated. At their closest approach, the two stars are roughly 8 astronomical units apart, about the distance from the Sun to Saturn. At their widest, they are roughly 31.5 astronomical units apart, farther than Neptune is from the Sun. And then back again in a patient 50-year waltz. Think about what that means for the system. At closest approach, Sirius B is exerting a significant gravitational pull on Sirius A, tugging it noticeably sideways. At farthest separation, the pull is weaker, more distant, but never absent. Over decades, a careful observer with precise measurements can watch Sirius A's path across the sky slow its wobble and then speed it again as the companion nears and recedes. The orbit was mapped, refined, and confirmed through the latter half of the 19th century and through the 20th, with each generation of better measurements tightening the model. And all of it traceable in the end to Bessel's initial observation that the path of Sirius was not straight, that it wobbled slightly in a rhythm that pointed unmistakably to a hidden companion. The pup is there, it always was, you just had to know how to look. And here is the part of the story that most people never hear. Because everything we have talked about so far, the wobble, the conformation, the dead star the size of the Earth, the teaspoon that weighs tons, all of it has been about Sirius B as it is now, a white dwarf, a cooling cinder, the pup. But the pup was not always small. And this is where the story takes a turn that still feels, to me, quietly astonishing. Because the companion and the one hiding in the glare, the one Bessel found on paper and Clarke found through glass, was once the biggest star of the pair. Let that settle in for a moment if you are still awake enough to let it. Right now, when you look up at Sirius, that blazing blue-white point in the winter sky, the brightest thing up there by a wide margin, what you are seeing is Sirius A, the survivor. The one still fusing hydrogen in its core, still burning, still in the full flood of its main sequence life. Sirius A is about twice the mass of our Sun, 25 times more luminous, and by the reckoning of stellar physics, it has a good couple of billion years left in it. It is young, it is vigorous, it is, in the language of astronomy, still living. But the pup, Sirius B, the tiny, hot, invisible, impossibly dense companion, was once the greater of the two. When this system formed roughly 230 to 250 million years ago, back when dinosaurs were still tens of millions of years in the future, when the continents were arranged in shapes we would barely recognize, the two stars condensed out of the same cloud of gas and dust, siblings born from the same molecular nursery. And the star that would become Sirius B was the heavier one. By a significant margin, it is estimated that the original Sirius B, before its transformation, carried somewhere around 5 solar masses, 5 times the mass of the Sun. Compared to Sirius A's 2 solar masses, it was the dominant partner, the bright one, the loud one. If anything in that young system deserved the name the primary star, it was the star that is now the pup. And that is the quiet irony at the heart of this system. In stellar physics, mass is destiny now, but not in the way you might expect. You might assume that being heavier means lasting longer, that a more massive star has more fuel and therefore more time. But it works the other way around. A more massive star burns through its hydrogen at a far higher rate. Gravity squeezes its core harder, temperatures run hotter, fusion races faster, and the fuel disappears at a rate that outpaces the extra supply completely. A star 5 times the mass of the Sun does not live 5 times as long. It lives a fraction as long. Our Sun will likely spend about 10 billion years on the main sequence. A star of 5 solar masses burns through its core hydrogen in something more like 100 million years. A brief, brilliant life, fast and fierce and finished. And so the original Sirius B, the heavy one, the dominant one, ran through its fuel first. It had been fusing hydrogen in its core for something like 120 million years, and then the hydrogen ran out. What happened next is a process that has played out billions of times across the galaxy, a story the universe tells over and over. When a star exhausts its core hydrogen, the fusion that has been holding it up against its own gravity falters. The core contracts under gravity, heating up till it becomes hot enough to fuse helium instead. But the outer layers, no longer supported in the same way, begin to expand. The star swells. It cools at the surface as it grows. It becomes enormous. Red. Bloated. A red giant. Imagine Sirius B at this stage. A star of perhaps 2 to 3 solar radii on the main sequence, transformed into something vast and ruddy, swollen to perhaps 100 times its original size, blazing with a red-orange glow that would have been genuinely spectacular from anywhere in this part of the galaxy. And Sirius A, still a young star, still burning steadily on the main sequence, its companion, now this enormous red beacon, dominating their shared sky. This phase does not last long, cosmically speaking. Red giants are a transitional state, the final flourishing before the end. The helium in the core eventually runs out too, and for a star in this mass range, not heavy enough to continue fusing carbon and beyond, that is the end of the nuclear road. What happens then is, in its own way, beautiful. The outer layers of the star are shed. Gently, over tens of thousands of years, the star releases its outer envelope in a slow, expanding shell of gas and dust, lit from within by the still hot remnant core. This is a planetary nebula, a glowing shell of material, often in intricate shapes, beautiful enough that astronomers have been photographing them and marveling at them for well over a century. The name is slightly misleading, a historical accident from early telescopes when these objects looked vaguely like planets through small apertures. They have nothing to do with planets, they are the discarded skins of dying stars, illuminated like lanterns in the dark. And left behind when the nebula has drifted away and thinned into the interstellar medium is the naked core. That exposed core is the white dwarf. It is what used to be the beating heart of the star, the place where fusion happened, stripped of everything surrounding it, compressed by gravity to a small, dense, incredibly hot remnant. And it no longer fuses anything. Its nuclear life is over. It has nothing left to burn. That core is Sirius B, the pup, the object Bessel deduced mathematically in 1844 and Alvan Graham Clark found through his new lens on January the 31st, 1862. The system is estimated to be around 230 to 250 million years old. Sirius B is thought to have completed its main sequenced life roughly 120 million years ago. It has been a white dwarf since then, cooling, slowly, patiently, over a span of time longer than the entire age of the dinosaurs. It began cooling perhaps around the time the Jurassic period was drawing to a close, and it is still cooling now as you lie there listening. It has a long way to go yet. White dwarfs are extraordinarily poor at releasing their heat. Their tiny surface area bleeds away energy slowly, and models suggest Sirius B will remain detectable for billions more years, gradually dimming, eventually fading to what theorists call a black dwarf. Though the universe is not yet old enough for any black dwarf to have formed, even the oldest white dwarfs are still faintly glowing. The corpse is patient. And now here is a question that might be drifting into your mind as you rest. If the white dwarf is not burning, if it has no fusion, if there is no fire left, what stops it from collapsing? What keeps that sun's mass from crushing inward under its own gravity into something smaller still? We touched on the answer earlier: electron degeneracy pressure, the quantum mechanical phenomenon Ralph Fowler worked out in 1926. But there is a deeper layer to this answer, and it involves a limit, a ceiling, a maximum weight that a white dwarf can carry. It was worked out in the early 1930s by a young Indian physicist named Subrahmanyan Chandrasekhar, and the story of how he arrived at it is itself a piece of history worth knowing. Chandrasekhar was 20 years old when he set sail from India to England in 1930, heading to Cambridge to continue his studies. On the voyage, to pass the time, he began working through the mathematics of white dwarfs. He had been thinking about electron degeneracy, the quantum pressure that holds these objects up, and he wanted to understand whether it could hold against any mass at all, or whether there was a breaking point. What he discovered working through the equations over those weeks at sea was that there is a breaking point. If you pile enough mass onto a white dwarf, the electrons are forced to move faster and faster to maintain their exclusion from each other, and eventually they approach the speed of light. At that point, relativistic effects kick in, and the degeneracy pressure can no longer keep up with the increasing gravity. The electrons lose the fight. The star collapses. The mass at which this happens is approximately 1.4 times the mass of the Sun, 1.4 solar masses. That is the Chandrasekhar limit, named for the young man who calculated it on a steamship as the Indian Ocean passed beneath him. Sirius B sits at around 1 solar mass, 1.0, perhaps 1.02. It is comfortably below the limit. The electron degeneracy pressure holding it up has plenty of margin. It will not cross that threshold. It will simply cool very slowly for an immensely long time. But the limit matters for other reasons, because it tells you what happens when stars die in ways that don't leave a safe white dwarf. When a star is massive enough and its remnant core exceeds 1.4 solar masses, the electrons cannot hold. The core collapses inward with tremendous violence. What you get instead of a white dwarf is a neutron star, an object where electrons and protons are crushed together into neutrons, and the whole stellar core, perhaps 1 to 2 solar masses, is compressed into a sphere perhaps 20 kilometers across. 20 kilometers, the radius of a small city. And if the remnant is heavier still, even neutron degeneracy fails, and the collapse continues without stopping into a black hole. So the Chandrasekhar limit is not just a footnote about one white dwarf, it is the branching point. Below 1.4 solar masses, you get the pup, a cooling crystal of degenerate matter, manageable, stable, old. Above it, you get something far stranger. The limit is the difference between a quiet death and a catastrophic one. Subrahmanyan Chandrasekhar received the Nobel Prize in Physics in 1983, partly for this work, nearly 50 years after he first derived it. There had been resistance to his ideas early on, some of it quite fierce. The great Arthur Eddington publicly dismissed the idea that a star could collapse beyond a white dwarf as absurd. History has been unkind to that dismissal. Now, Sirius B is not only extraordinarily dense, it is also, in a way that surprises people, extraordinarily hot. We have mentioned this already, but it is worth lingering on because it runs so counter to the intuition that dead means cold. The surface of Sirius B is around 25,000 Kelvin. For comparison, the surface of our Sun, the living, fusing, burning Sun, is around 5,800 Kelvin. The pup is more than 4 times hotter at its surface than the Sun, and yet it is faint. Invisible to the naked eye, drowned in the glare of its companion. This seems like a contradiction until you think about what drives a star's luminosity. A star's brightness depends on 2 things: how hot its surface is and how large its surface area is. The Sun is roughly 100 times the radius of the Earth. Its surface area is enormous, and heat pours off it from every direction across that vast sphere. Sirius B has a radius of roughly 5,800 kilometers, slightly smaller than the Earth. Its surface area is tiny. Even though each square meter of its surface is blazing at 25,000 Kelvin, there are so few square meters total that the total output of light is very small compared to any normal star. Hot but dim. A tiny, fierce thing radiating furiously from a pinprick of surface. And besides Sirius A, which is itself 25 times more luminous than the Sun, one of the genuinely bright stars in its own right, Sirius B is essentially invisible. Sirius A outshines it by a factor of roughly 10,000 in visible light, 10,000 to 1. Which is why, even after Bessel published his calculation in 1844, and even after the astronomical community accepted that there probably was something there, actually seeing it was nearly impossible. The glare was overwhelming. You needed either a very good telescope and very good seeing conditions, or you needed to wait for an orbital configuration that moved the companion far enough away from the primary, in angular terms, to be separable. And when Alvan Clark found it in 1862, he was using what was then the most powerful refractor in the United States, the 18.5-inch lens his father's firm had just finished, and it still required knowing exactly where to look. The pup was hiding in the most obvious hiding place in the sky, right next to the brightest star, drowned in its light. There is something almost poetic about that. The thing that draws every eye, the one point in the winter sky you cannot miss, was the thing that had been obscuring the secret all along. Now let us spend a moment with the light itself. When light climbs out of a gravitational field, it loses energy. Not in a dramatic way that you would ever notice on Earth. Our gravity is too gentle, but around an object with Sirius B's surface gravity, more than 100,000 times Earth's, the effect becomes measurable. The light is shifted slightly toward the red end of the spectrum. Not because the source is physically moving away, but because each photon is climbing out of a deep gravitational well, and that climb costs energy, and in light, less energy means longer wavelength, and longer wavelength means redder. This is gravitational redshift, a prediction that falls directly out of Einstein's general theory of relativity. Einstein published that theory in 1915, and by the early 1920s, astronomers were already eager to test its predictions on the densest objects they knew about. Walter Sidney Adams, working at the Mount Wilson Observatory in California, attempted to measure the gravitational redshift of Sirius B's light in 1925. The measurement was extraordinarily difficult. You are trying to tease apart a tiny wavelength shift from the general blurring caused by proximity to a brilliant companion. And Adams's result was encouraging, but not definitive. He found a shift roughly in line with what general relativity predicted for a white dwarf of Sirius B's mass and size, but the precision was limited by the instruments of the era. The definitive measurement came much later, in 2005, when the Hubble Space Telescope was turned on Sirius B. Above the atmosphere, without the blurring and scattering of air, the Hubble could resolve the light from Sirius B cleanly and measure its spectrum with precision that Adams could not have dreamed of. And the result matched. The gravitational redshift was exactly what general relativity predicted for a star of approximately 1 solar mass packed into a radius of about 5,800 kilometers. The intense surface gravity was confirmed not by touching Sirius B, not by sending any instrument there, but by measuring the color of its light. Einstein's equations, written in a Berlin study in the years around the First World War, describe a dead star 8.6 light-years away, with enough precision that we can confirm them from orbit. That still strikes me every time I think about it as one of the more remarkable things in science. Not just that the prediction was right, but the chain of reasoning from abstract mathematics to measurable starlight that proved it. Now, there have been other things said about Sirius B over the years, other claims, and because this is a long night and a quiet one, and because some of these claims float around the edges of what people read about Sirius, it seems right to address them gently and honestly. The first is the matter of color. Some ancient and medieval sources, among them the Egyptian-Greek astronomer Ptolemy in the 2nd century, the Roman writer Seneca, and certain Chinese astronomical records, describe Sirius as reddish, ruddy, not the blue-white brilliance we see today. And for a long time, this was a puzzle that attracted serious astronomical attention. Could it be that Sirius B was once visible to the naked eye as a red giant in historical times within the last 2,000 or 3,000 years, and that ancient observers were recording not Sirius A but the companion in its dying red phase? The physics does not allow it. Sirius B completed its red giant phase and became a white dwarf roughly 120 million years ago. Not 2,000 years ago, not 10,000 years ago, 120 million. The red giant that seeded the pup was burning in the Jurassic skies. No human eye watched it, no papyrus recorded it. The gap between when it actually happened and when Ptolemy was writing is on the order of 100 million years. The ancient descriptions of a red Sirius are most likely explained by something much more prosaic. When Sirius is near the horizon, rising or setting, it is seen through a much thicker slice of atmosphere. That atmosphere scatters the blue light away, just as it does with the sun at sunset. A bright blue-white star near the horizon can appear distinctly reddish or orange. Ancient observers watching Sirius in its heliacal rising might have been watching it at precisely that atmospheric disadvantage. There may also be translation and transcription issues, the possibility of confusion with other nearby stars, and the general difficulty of ancient color vocabulary. Some scholars argue the ancient color terms simply do not map onto our modern spectrum categories the way we assume. It is a solved puzzle, or close enough to one. Not evidence of a star dying in historical time. The second claim is more colorful and, in some circles, more persistent. In the 1970s, a researcher named Robert Temple published a book called The Sirius Mystery. In it, he argued that the Dogon people of Mali in West Africa possessed ancient astronomical knowledge about Sirius B, its existence as an invisible companion, its high density, its orbital period, knowledge that they could not have acquired through naked eye observation, since Sirius B is invisible without a telescope. Temple's argument was that this knowledge must have come from an ancient visit by extraterrestrials. It is a vivid idea, and it is not well supported by the evidence. The Dogon were studied by French anthropologists Marcel Griaule and Germaine Dieterlen in the 1930s and 40s, and it was their fieldwork that recorded the astronomical claims. But there are significant problems. The information about Sirius B and its density was not written down before Griaule's visits. It was reported by Griaule after his visits. The Dogon had extensive contact with Europeans and with the educated world well before the anthropologists arrived. Missionaries, traders, colonial administrators, The information could very easily have been absorbed from any number of external sources and incorporated into oral tradition. And in the decades since Temple's book, researchers who have visited the Dogon and asked about these astronomical claims have found that the knowledge is not uniformly held, that many Dogon are unaware of it, and that the complexity attributed to it may be a result of how Griol asked questions, sometimes quite leading questions, as much as a result of what the Dogon knew independently. This is not a reflection on the Dogon as a culture or a people. Their cosmology is rich, their traditions are deep, and their knowledge of the night sky that they could observe is real. It is a reflection on the specific claim that they possessed secret astronomical knowledge about an invisible star before modern telescopy. The evidence does not hold up. The most likely explanation is that the astronomical knowledge in those accounts came from European contact, directly or indirectly. There is no ancient astronomical mystery about Sirius B. There is, however, a real one, the one Bessel uncovered, the one Clark confirmed, the one that took 18 years to go from a wobbly line on paper to a pinprick of light through a new glass. That story is true, verified, and to my mind far more interesting than any legend. And then there is the phantom. In the decades following Clark's discovery of the pup, various observers reported what seemed to be evidence of a third body in the Sirius system, orbital perturbations that the two-body model didn't quite account for, a hypothetical Sirius C. It was taken seriously enough to be written about and investigated through the 1920s, again in the 70s, and again in the 90s. High-precision observations, including those made with the Hubble Space Telescope, have found no evidence of a third body. The Sirius system is a binary, two stars, the pup and Sirius A alone in their eccentric 50-year dance. The orbital measurements, when done with modern precision, fit the two-body model cleanly. Sirius C almost certainly does not exist. It is worth saying that simply, because the internet still carries the claim in various forms dressed up in varying degrees of certainty. There is no Sirius C, there is Sirius A, there is the pup, and there is space. Now, one more small and rather lovely fact before we gather everything together. Sirius is moving toward us. It is not static against the background of space as stars might seem. It has a proper motion, a real velocity relative to the solar system, and right now, that motion is carrying it gradually in our direction. It is already the seventh nearest known stellar system to us, and it will get nearer still. Over the next 60,000 years or so, Sirius will continue brightening, not dramatically from year to year. The change in any human lifetime is imperceptible, but on the long scale of geological time, the star will grow brighter, closer, and then, once it has passed its closest point, it will begin to recede again, gradually fading over another long span of millennia. 60,000 years, more than 3 times the span of all recorded human history, and in that time the sky will still carry Sirius, just a little brighter with each passing age, watched by whatever beings are watching by then. Human civilizations have been watching Sirius for at least 5,000 years that we can document. The ancient Egyptians paid extraordinary attention to it. For them, it was not just a star. It was a calendar, a promise, a deity. The goddess Sopdet, whom the Greeks called Sothis, was Sirius made divine. And the event that mattered most was the heliacal rising, that moment once a year when Sirius first became visible above the eastern horizon just before dawn, after a period of weeks when it had been invisible, lost in the sun's glare on the other side of the sky. The heliacal rising of Sirius, in the ancient Egyptian calendar, preceded the annual flooding of the Nile by a matter of weeks. The Nile flood, which deposited fertile silt across the fields and made Egyptian agriculture possible, was in many ways the heartbeat of the civilization. and Sirius was the herald. When Sopdet rose in the east before sunrise, the farmers knew the flood is coming. Prepare. The star was woven into the Egyptian calendar, into their temples' orientations, into their year. The so-called Sothic cycle, a period of roughly 1,460 years that arose from the slight mismatch between the Egyptian civil calendar and the astronomical year, that was named after the star. Sirius was not background scenery, it was time itself. And the Romans inherited something from this, translated through Greek culture. Sirius is the alpha star of Canis Major, the greater dog, the faithful dog at the heels of Orion the hunter. And the Greco-Roman world knew that when Sirius rose with the sun in summer, the hottest, most oppressive days of the year tended to arrive. They called this period the dies caniculares, the dog days. The days of the dog star, we still use that phrase today. The dog days of summer. The phrase is older than the Roman Empire. It comes from this star, from that blue-white fire in Canis Major, from a tradition of watching the sky that stretches back to before writing, before cities, before most things we would call civilization. 5,000 years at minimum of human eyes finding Sirius in the dark. And in all of that time, through Sopdet and the heliacal rising, through the dog days, through every winter night, a person has stood outside and looked up and noticed that one blazing point, not one of them knew. Not one of them knew that half of what they were seeing was a corpse. Not one of them knew that the light reaching their eyes was not from one source but from a system, a pair, and that the junior partner of that pair was a sun's worth of matter crushed into the size of a planet, held up by a quantum rule that no one would understand for another 100 years, dense enough that a teaspoon of it would break a scale designed for cars. They watched it rise, they used it to know when to plant, when to flood, when to brace for summer. They made it into a goddess and named it after a dog and built temples that aligned with its position. And all the while, the pup was there, invisible, patient, orbiting in its eccentric 50-year path, cycling between the distance of Saturn and the distance of Neptune, unseen because Sirius A is 10,000 times brighter, and the two are packed so close together on the sky that no ancient eye and no telescope for 18 centuries could pull them apart. Bessel saw the wobble in 1844, and for 18 years the pup existed only as a number, a period, a mass, an invisible companion inferred from mathematics, from the logic of gravity, from the simple insistence that a path which is not straight must be being bent by something. And then, on the last night of January 1862, Alvan Graham Clark aimed a new lens at the brightest star in the sky and found a faint companion exactly where the numbers said it would be. The body was there all along. Bessel had read the death certificate. Clark found the body. The brightest point in our night sky is half corpse, the thing everyone sees, the thing children notice and point at and ask about, the thing that has served as calendar and deity and omen for longer than most languages have existed. It is a binary system, a living star and a dead one, fire and cinder, youth and an ancient cooling remnant orbiting each other in an eccentric dance that takes 50 years to complete, moving together through space, approaching us slowly, brightening over the long arc of geological time. The pup is there right now. If you could pull back the glare of Sirius A, if you could somehow block that 10,000-fold flood of light, you would see a tiny, fierce, blue-white point, 4 times hotter than the sun at its surface, but so small it barely shows. Surface gravity more than 100,000 times what presses you down into your bed right now. A place where the very concept of standing, of weight, of solidity becomes meaningless. A teaspoon of it would weigh several tons. The light that leaves its surface has to climb out of a gravitational well so deep that Einstein's equations can measure the toll it takes, and have been confirmed to do so in 2005 by a telescope above our atmosphere. And it is not going anywhere. It is cooling very slowly, 1 quiet degree at a time, over billions of years. Eventually it will be called a black dwarf, a dark, cold, inert lump of degenerate matter, the final state of a thing that was once a star, 5 times the mass of our Sun. But not yet, not for a span of time so large it swallows all of human history 1,000,000 times over. For now the pup glows, a white dwarf, a hot remnant, the exposed core of something that died 120 million years ago, before the dinosaurs were gone, before the Himalayas had risen, before almost everything we would recognize about the world took its current shape. It is one of the oldest neighbors we have in stellar terms, 8.6 light-years away, close enough that the light you are imagining right now left its surface 8.5 years ago, before your alarm went off this morning, before this year began, before whatever you were worried about yesterday had even fully formed. That light is already here. You have been circling all of this with me slowly over this quiet night. We started with a weight, a teaspoon that would buckle a kitchen scale, and worked our way to this. To a system 250 million years old, half alive and half dead, watched by every culture that has ever looked south in winter, known as a goddess and a calendar and a seasonal clock, and understood as a binary, as a grave beside a living fire. Only in the last 160 years, Bessel gave us the wobble. Clark gave us the sighting. Fowler and Pauly gave us the reason it doesn't collapse. Chandrasekhar gave us the limit, the boundary between a quiet death and a violent one. Adams and then Hubble gave us Einstein's fingerprint on the light itself. And from all of it, a picture assembles. Not of a single bright star, not of a simple point of light, but of a system in time, a system that was young when the world was different, that will still be here when the world is different again, that carries inside it a dead companion heavier than the sun, dancing around the living one in an oval orbit that swings wide as Neptune and closes as tight as Saturn, over and over every 50 years. You are out there somewhere tonight, lying down or resting or half asleep already, in a house or a flat on a night that might be cold or warm, with a lamp still on or a room gone dark. And somewhere above you, whether you can see it or not, whether there are clouds or clear sky, Sirius is there, maybe already below your horizon, maybe still climbing, maybe shining hard and bright and blue-white in the dark above, wherever you are. And it is two things, it is always two things. A living star and its dead companion, the brightest and the invisible, the flame and the cooling cinder, the one every human generation has known and named, and the one that waited patiently behind the glare for 18 years after a man in Germany proved it had to be there. We found it. We weighed it, we measured it, we read its temperature from afar. We confirmed Einstein's theory on its light. We know what it is made of and why it does not fall. We know how it was born and how long it has been cooling. We know the width of its orbit and the period of its dance and the number of solar masses packed into its Earth-sized sphere. And we know something that feels important to carry into sleep, that the universe hides things not because it is secretive, but because our senses are narrow. Bessel didn't need to see the pup to know it was there. He needed only patience, mathematics, and the willingness to trust that a wobbly line meant something real was pulling. The invisible things are real. The things you cannot see are sometimes the most significant ones. The corpse beside the flame is what makes the flame make sense. And you, wherever you are, Whatever corner of the night you are in, you are made of the same atoms that make up Sirius B. The same carbon, the same oxygen, the same heavier elements that got scattered into space when stars far older than Sirius shed their outer layers as planetary nebulae, drifted through the galaxy, and eventually collapsed into the cloud that became the solar system. We are, in a very literal sense, downstream from events like the one that made the pup. That is not poetry, that is chemistry. It is a good thing to carry into sleep if this slow walk through the dark helped you rest or kept you up a little longer than you intended, which I warned you might happen, and I do apologize for that. A gentle like or subscribe helps this sleepy little channel more than you might think. Small creators like me really do rely on it to keep making these long, quiet nights possible. And if you'd like to tell me where you're listening from tonight and what time it is in your corner of the world, I would love to know. That question is always genuine. We've been drifting together through a system 250 million years old, through a detective story that took 18 years to close, through the quantum reason a dead star refuses to fall. Take it with you. Calm mind, clever dreams. I'll be here tomorrow night.